In today's note, we're going to look at connections between continuous random variables and discrete random variables. So continuous random variables has been what we've been looking at this unit, and discrete random variables is what we've looked at in the past. So if we can recall, going back to normal or binomial distribution, distribution involves independent trials with just two results, either a success or failure. And the probability of an event occurring exactly x number of times is equivalent to the probability of x is equal to n choose x times p to the power of x times q to the power of n minus x. And we've also seen this written as nx p to the power of x q to n minus x, where n is equal to the number of trials / data, x is equal to the number of specific outcomes you want, p is equal to the probability of success, which we've talked about in the last note, and q is the probability of failure. So this is from our note on, or our unit on probability distributions. So if I consider the probability distribution for the number of heads in one cost of a fair coin, the probability of getting either 0 heads is 50%, and the probability of getting 1 head is 50%. So this would be an example of uniform distribution. Because all outcomes are equally likely. And we can see that because it does form the shape of a box. So remember, if our data forms the shape of a box, it means it's uniform. So graphing all of the possible binomial probabilities related to an event creates a binomial distribution. And if we consider the following distributions of tossing, the first graph looks at the number of heads on 2 tosses. The second one looks at the number of heads on 4 tosses. And what we want to describe both distributions. If I look at the first graph, and I can see kind of by the general shape in green, I have my mean down the middle. What this looks like is it looks almost like a normal distribution. And when I look at the next one, where I'm looking at 4 tosses, I can see it becomes to look more normal. And what I mean by more normal is that it fits that shape of a bell curve. So in example 2, what I want to do is go through and complete the table for a graph and graph it for 6 tosses. So here I'm looking at the same idea, tossing a coin 6 times, and I want to determine the probability for getting heads. So for 0, it's 6 outcomes, or 6 total trials, choosing 0, times 0.5 to the power of 0, times 0.5 to the power of 6. Basically, again, this is just our probability formula for binomial distribution. The same formula that we've seen before. In this case, n is equal to 6. Probability of success is 0.5. Probability of failure is also 0.5. So when I go through and I complete all these calculations, it's 0.0 0, 1, 5, 6. So when I go through and I calculate all the probabilities for each number of outcomes, these are the values that I should get. So basically you're just going through and completing these calculations. When I then go and I graph them, what I should get is I should get something that looks similar to this. So the probability of getting 0, 1, 2, 3, 4, 5, and 6 heads on 6 rolls. And what we can see here is this clearly forms now a more normal distribution, with the probability or the mean or median being in the middle with a few outliers on either end. So if I want to describe the distribution, I could describe it as a normal distribution. So in conclusion, as the number of trials in a binomial experiment increase, because again we've seen examples where there's only one roll or one toss, then 3, or then 2, then 4, then 6. So as the number of trials in a binomial experiment increase, the binomial distribution tends to a normal distribution. So the more trials I do, the more likely the distribution becomes a normal distribution. Because binomial distributions are normally distributed, or they become normally distributed, we can use z-scores to approximate the total probability of a large range of separate probabilities. So we can only use binomial approximation, or using the z-scores, similar to what we've done so far in this unit, if there is enough data. If there is not enough data, so again this is the key thing, is if there is enough data. If there isn't enough data, we have to use this formula and use the tables to figure it out. And there are some steps that we can use in order to check this out. So the first step, check to see if there is enough data. And the way we do that is by doing either n times p and hoping that it is greater than 5, and n times q, and checking to see if that is greater than 5. If we do those two things and they're greater than 5, there's enough data for us to use. So we also need to find the mean, which is just n times p, and standard deviation, which is the square root of n times p times q. We then need to determine the x value that we're looking at. And with our x value, we have to add plus or minus 0.5 to it for continuity correction. Basically, because we're looking at a discrete situation and we need to change it to become continuous or use continuous intervals for the normal approximation. So again, using the z-scores or normal distribution requires continuous variables, but usually this data that we're going to be using is going to be discrete, so we need to ensure that we are treating the discrete variables as continuous. From there, we find our z-score, so the value minus the mean divided by the standard deviation, and then with our z-score we use our z-score table or the chart in the note or in the textbook to find a probability. So in example 2, a bank found that 24% of its small business loans become delinquent. If 200 small businesses are selected randomly from the bank files, what is the probability that at least 60 are delinquent? So what we want to look at first, we are dealing with a binomial distribution. The bank loans are either delinquent or they're not. So we need to determine the probability that at least 60 are delinquent. So this would be very time consuming to do in a table because we'd have to do 60, then 61, 62, all the way up to 200. but we can check to see if we can use a normal distribution to approximate this. The first step that we have to do is to check to see if there's enough data. So if we look at n times p and n times q, I'm going to use these two values to help me determine if there's enough data. So n times p, n is 200, times p is 0.24, probability of success, and I get 48. N times q, 200 times 0.76 is equal to 152. So you may have been wondering why I use 0.24 as a probability of success, even though we're talking about delinquent, and delinquent doesn't necessarily mean a success. We have to keep in mind a success is what we're looking for. In this case, I'm looking for the probability that they're going to become delinquent. So in this case, what's considered a success is the fact that they're delinquent. So P and Q are both greater than 5. So that means that we can use normal distribution to approximate the probability. For now, we need to then figure out our mean, which is n times p, and our standard deviation, which is equal to square root of n times p times q. So n times p, 48, which we've already done. So 200 times 0.24 works out to 48. And for standard deviation, 200 times 0.24 times 0.76, all square rooted, is equal to 6.04. Now, we need to find our z-score, but before we do that, we need to take our value up here, our x value, and turn this into a continuous variable. So the discrete form, or this means at least, so this means 60 above. So if we want to turn this into a discrete or a continuous variable, right now it's discrete, which means 60, but when we're looking at it as a continuous variable, because we mean 60 or greater, we're going to turn this 60 into plus or minus 0.5. So in this case, I'm going to turn it into 59.5, because this way, by subtracting that 0.5, my interval will now include the 60 that I'm looking for. So now I can find my probability. So the probability that x is greater than or equal to 59.5. This is now a continuous variable. I can do 59.5 minus the mean, which is 48, divided by the standard deviation, 6.04, and I get a z-score of 1.90. With my z-score, I'm going to go to my table, and I'm going to find the probability of the value, that a value is less than or equal to 59.5, because again, remember the probability table tells us the value equal to or less than. So in this case, it is 0.9713. Again, if I'm looking at a normal distribution, I have my mean down here. I have my mean in the middle. 1.9 is up here. Or in other words, 48 my mean, and then 59.5. And what I'm trying to find is I want everything from here on, but everything from that line and back is what the table gives. So I need to use a little bit of indirect method here. So the probability that x is greater than or equal to 59.5 is equal to 1 minus the probability that it is less than. So in this case, it's 1 minus 0.9713, and I get the probability is 0.0287. So therefore, the probability of at least 60, or probably at least 60 delinquent, is 2.87%. So if we look at this entire example, we had to first again make sure we had enough data to use a normal approximation. We then determined the mean and a standard deviation. We then found our z-score using a data value that was turned from discrete to continuous. And then we used indirect method to determine exactly what we want because we were looking for 60 and above. If I want to find that exactly 60 of them are delinquent, again, I could use the probability formula, but I'm going to show you how to do it using a normal approximation. So because I'm looking for exactly 50 or exactly 60, that means I want to turn this into a continuous variable. So right now it's discrete and it's at 60. If I want it at more than 60, my continuous, I have to change it to make it an interval. So that means it will be 59.5 to 60.5. That's going to be my continuous value that I'm looking for because that range encompasses or makes it exactly 60. So in this case, I have to go through and determine my z-scores. The one z-score I already got from 59.5. 59.5 minus the mean, which is 48, divided by 6.04. And I got a value of 1.90, so that was on the last question. My other z-score, 60.5 minus 48 divided by 6.04. I get a value of 2.07. So now what I can do is I can determine the probability, 59.5 x is in the middle, 60.5. Basically what I'm doing is I need to take the probability that z is less than 2.07, subtract it from the probability with the z-score of less than 1.90. So I go to my chart, probability that z with the z-score of less of 2.07 and less is 0.9808. I'm going to subtract z-score of 1.9, which is 0.9713. And I get a final value of 0.0095. Again, if I want to visualize this, I have my normal distribution, I have my mean, I'm looking for a z-score of 1.9, another z-score of 2.07. And I want to find 2.07 gives me from this value all the way back 1.9 gives me from this value all the way back. But what I'm really looking for is this interval value. What is the probability in here? Is what I'm looking for, which was what I found. So in the end, therefore, the probability that exactly 60 are delinquent is 0.95%. So the key thing from this note that we want to take or get is that in some cases we can take discrete variables and use a normal approximation to determine the probability, especially when there's a lot of values or a lot of trials, which would make it difficult to create the table for a binomial distribution and go through and add up the probabilities for each individual case. So we just need to remember our steps to walk through how to determine the probability using normal approximation.